So, good morning, good afternoon, and good evening, everyone. I'm Chintan Shah, and I'm going to talk about laboratory X-ray studies with trapped ions using electron beam ion traps and synchrotrons. So, one of the very first problem that I'm going to talk about is iron 16 plus line emission problem. Lee already mentions some kind of a brief introduction to this problem. So, as we all know, iron 16 plus ion emits strongest soft X-ray lines seen in the space, and these are the strongest line complexes: 2p3d complex and 2p3s complex. This 2p3d complex contains line 3c, a resonance line, and 3d, an intercombination line, and also this 2p3s contains this highly crucial forbidden line. And the line ratio of this resonance to forbidden line or resonance to intercombination line 3c and 3d are highly crucial to determine plasma temperature, densities, turbulence velocity, resonance scattering, and different plasma diagnostics parameter. However, from last 40 years, we see some sort of a disagreement between the observations and the model, and also between the experiments and different theoretical calculations. So what you see here is the 3C3D intensity, line intensity ratio. There are several experiments done at Princeton tokamak here, several experiments performed at Lawrence Livermore electron beam ion trap, which are here, and also few observations from the Sun and Capella. And on the top of it, you see on this gray squares several 3C 3D values from the calculation and model. And what you can see that the calculated and the model values are consistently higher than any of the experimental value or from the observation. So what exactly is going on? Is the theory wrong or the model? And if it is, then which part exactly? So as actually Lee also mentioned in his talk that there have been plenty of experiments done at the Lawrence Livermore electron beam ion trap and at Heidelberg electron beam ion trap. And here with the electron beam ion trap, usually the electron beam is the one which drives the ionization, excitation, and recombination processes, and also it simultaneously traps the ion. And with the collisionally excited ions in the center of the trap, actually, as it was mentioned in the previous talk, that we can measure several different cross sections and line formation mechanisms like dielectronic recombination, direct excitation, and the resonant excitation, and so on. And as all of this experiment has showed some sort of still a disagreement with the 3C 3D ratio or 3S to 3D ratio. So what we did next was the laser spectroscopy. So the key advantage of the laser spectroscopy is that we can have a purely photonic excitation, which will suppress any uncertainties if they are arising due to this collisional excitation process. So the measurement technique is very simple, that we produce and trap the ions in our EBIT of our choice, and then we shine the laser on these trapped ions and photo excite these ions and let them fluorescence, and simply we can detect this fluorescence with the typical X-ray detector as a function of laser wavelength. This laser wavelength we can actually select by scanning this monochromator. So to do this experiment, we went to LCLS in Stanford. So this is a 3 to 4 kilometer long LCLS beamline where you have an injector and LINAC, which accelerates the electron bunches, and then electron beam transport system, and the undulator where electron bunches are forces to wiggle up and down in the magnetic field, and also forces to emit soft X-rays. And those soft X-rays we can actually receive near to this end station in the experimental hall where we parked our electron beam ion trap. So this is our flash EBIT from Heidelberg at LCLS in Stanford. So the soft X-ray beam comes from comes from the right here, and then enters to our EBIT from the collector side, and the photo excites the ion in the center of the trap. And the measurement technique is the same as I mentioned before, that we produce and store the ions in our trap, iron 16 plus and 15 plus, and then we can simply photo excite line 3C and 3D by selecting a different energy on the monochromator. And this is the typical plot we record. This is the fluorescence photon energy, which is recorded with this X-ray detector. And on the x-axis, you can see FEL photon energy, which we record with the monochromator. And you can see that at 812, we photo excite line 3D, and 826, we photo excite line 3C. And since both of these line are purely photo excited, we can take the intensity ratio of these two line, and that would be proportional to the oscillator strength of this line. And this is what we found out, that the experimental value of the oscillator strength of 3C and 3D was 2.6 plus or minus 0.23. We compare with the various theoretical calculations and values from the databases. All of them were in the disagreement, and the disagreements was roughly with the best theory at that time was 3 sigma. So we thought that we solved this experiment, solves serious old problem, and the conclusion was that the inaccurately predicted oscillator strength of 3C and 3D are the root cause between this long-standing 40-year-old discrepancy between the observations and the measurement. However, later on, there were serious shortcoming of the experiments, and theoretical modeling were addressed by several groups. And what are these shortcomings? So the first one is the nonlinear dynamical effect. So what is this? Like when you have a femtosecond X-ray laser with the intensities about 10 to the 12 or 10 to the 13 volts per centimeter square, then the upper state level population of 3C and 3D in your photo excitation measurement will not reach to the equilibrium population. So this is what exactly is shown on the left hand side. This is the excited state population as a function of pulse duration of your laser at the intensity of 10 to the 12 volts per centimeter square. And you can see if, depending on the pulse duration, if you have a 50 femtosecond or 500 femtosecond, you can have a different excited population, which will also give you a different 3C3D intensity ratio. The other issue was the population transfer between the iron 15 plus and iron 16 plus. It has very strong autoionization channel, which feeds from the ground state of iron 16 plus to this 15 plus J is equal to 3/2 level, and which feeds to this line C around 812, which is usually blend with the line 3D. So this can also cause a problem. Both of these issues were mitigated in our another synchrotron campaign last year at Petra 3 in Hamburg. So here is the storage ring of Petra 3, and here at the in this several experimental hall. And we parked our electron beam ion trap at one of the P04 beam line. Here you can see the another EBIT, which is different than our LCLS beam time. This is a mini tabletop EBIT, which has a permanent magnet. And with this permanent magnet, this EBIT can still produce 0.9 Tesla magnetic field at the center of the trap, and it can also produce entrapped ions up to iron 24 plus. So we store our iron 16 plus, which is our ions of interest, and then we shine the synchrotron photon beam. It goes through the trapped ion here, and this is the fluorescence coming out of the ions, which we measure with the detector. And the good thing about the synchrotron photon beam is that the intensities are too low, which are roughly around 10 to the 5 volts per centimeter square. So we do not expect any nonlinear effect here. The another improvement we did was in the resolution. So what you see here is the 3C and 3D from the LCLS measurement, which had like roughly 1 EV, full width half maxima resolution at 825, which is very close to the Chandra high energy transmission grating also. Here we improved 10 times better. And with this 10 times better resolution, actually for the first time, we were able to resolve this line C from iron 15 plus from line 3D. So this also kind of, with the improvement in resolution, we also solve the problem related to this resonant population transfer between these two ionic species. So the measurement technique is the same. We receive the photons from the undulator. The mirror focuses on the grating. We scan the grating to excite different wavelengths and excite different photoions. And this is what we see, the same plot, fluorescence photon energy recorded with this fluorescence detector as a function of monochromator energy. You can see lines C and 3D are now nicely separated with the separation about 150 millielectron volts, so that now we can simply take the intensity ratios of line 3C and 3D without taking care of iron 15 plus contribution. And this is what we found out. The intensity ratio we found out was roughly around 3.1 plus or minus zero point 0.1. We compare with several experiments done at Lawrence Livermore, which are here. They are in good agreement. Also, several experiments at Princeton Tokamak in agreement. Also, several astrophysical observations. Here we have slightly lower value from our previous experiment at LCLS, which might be attributed to these two problems that I have told you. We compare our values with the different theories available from the literature, also 3C 3D ratios from different databases like NIST, SPACS, or AtomDB. All of them are still in disagreement. And we also did our own calculations with the distorted wave method to large scale configuration interactions to many body perturbation theory and different theoretical methods. And all of this theory converges roughly around 3.55, which is still phi sigma away from our experiment. So what we got from our recent campaign that we with this new experiment, we are reinstating this 40-year-old problem with the phi sigma discrepancy and 3% uncertainty, and the low oscillator strength are still a root cause of this long-standing problem. What can be done next from the experimental side? For this problem, actually we would like to investigate now the individual oscillator strength or natural line width of line 3C and 3D rather than their ratio. In last year, we actually already achieved the first step. We improved our resolution from 10,000 to 18,000. And with this improvement in the resolution, what you can see here already some sort of a Lorentz wing, which in the line 3C, which comes from the natural line width. However, we still have some problem to understand the instrumental profile at the P04 beamline at Petra 3. And we are planning to investigate this problem in the upcoming beam time. The second problem I want to talk about is the atomic oxygen velocity in the interstellar medium. And I think many of you guys have worked and aware of there are plenty of Chandra and XMM Newton observations of atomic oxygen 2p1s absorption in interstellar medium, which are sort of backlight by the bright extra binaries. This is one of the example spectra where you can see there are this strong line, atomic oxygen line, 1s2p transition around 23.5 angstrom. And here also you can see several observations, average from different sources. From Chandra, roughly around 527.4 electron volt, and from maximum Newton, the value is 527.3 electron volts. When all of these observations were compared with the high resolution laboratory measurement at advanced light source done a couple of years before, with this laboratory measurement, what we found out was some sort of a difference between the observations and the laboratory rest energy. And this difference was roughly around 500 to 600 millielectron volt. And if we treat this discrepancy between the laboratory rest energy and the line of sight average observed value from XMM and Chandra as a real astrophysical Doppler shift, then this would lead to a conclusion that atomic oxygen is moving away from us at the speed of 300 or 350 kilometers per second, which is sort of kind of a dubious conclusion. So what we found out that the atomic oxygen value from the ALS that was actually calibrated with the molecular oxygen Rydberg series, and the wavelength standards from the molecular oxygen Rydberg series comes from another experiment with the electron energy loss spectroscopy. And those experiments calibrated with another line and with the another line. So there are several chain of calibration which might have contributed to the issue with this atomic oxygen value which we got from the ALS. So to remove all of this issue with this calibration, we actually use the highly charged ions like helium and hydrogen, like oxygen and nitrogen, to calibrate first our synchrotron photon beam. And then we measure simultaneously oxygen Rydberg series, and then we recalibrate the atomic oxygen. And this is our experimental setup at BESI 2 in Berlin. The setup is very simple. We get the monochromatized X-rays from BESI 2. It enters to our EBIT, photo excites ions like hydrogen and helium, like nitrogen and oxygen, and then it leaves the EBIT and enters to the gas cell, where we fill this gas cell with the molecular oxygen. The photon beam simply photoionizes the molecular oxygen, and we measure with the channel electron photoions.
2 minutes, done.
Yeah, and this is the typical spectra that we get from the PolarX EBIT. This is the intensities as a function of monochromator energy, and we photoexcite helium like nitrogen. One is 5p transition and one is 6p transition, and also one is 7p transition. We simultaneously measure the oxygen Rydberg series, which is shown here in the black curve, and we recalibrate this oxygen molecular oxygen Rydberg series with this highly charged ions line 7p and 6p transition. And this is exactly what we found out. There is a systematic difference between the ALS value and our value at BESI. So you can see all of the feature from the molecular Rydberg series are shifted by somewhat 500 millielectron volt. And this is what we found out. The ALS value for the atomic oxygen was 526.79, and our value was roughly around 527.26. This exactly shows this difference what we see with the XMM and Chandra. So now new values from the lab are agreeing very well with the XMM and Chandra, and as we expect that atomic oxygen is not moving away from us at the speed of 300 kilometers per second. The very last topic, I would quickly go through it. We also did some photo excitation measurement in helium-like and lithium-like oxygen. And what you can see here is that we photo excite, and we can measure the excitation energy in helium-like oxygen, K alpha, K beta, K gamma, K delta, and so on, up to the series limit. And we can see again the same thing in the K beta 1 lithium-like. What we see here, this is the detected photon energy, which means that we photo excite the ground state of 1s squared 2s. This is the lithium-like oxygen, and it excites to 1s 2p 3p transition, and the 3p goes back to 1s and emits this X-rays, and this is what we see. In the K beta 2, actually, it was very interesting that we see the, of course, the direct decay channel back to the ground state from 3p to 1s, but we also see that there is another channel, so-called 2 electron 1 photon channel, which decays to 1s square 3s or 1s square 3d ground state. And similarly, we found out in lithium K delta that we do not see any direct decay channel. It is completely forbidden, and the complete photons are dominated by this 2 electron 1 photon transition. So what exactly is this transition is that, as I mentioned simply, that 1s square 2s is your initial lithium-like state. You excite the K shell electron to the 5p, your 1s 2s 5p, and what we expect that this electron will go back down because it's allowed transition. However, it doesn't do this. Here what happens that the 2s electron goes down, simultaneously the 5p electron goes to 4s, and it emits the photon roughly around 574 electron volts, which is 100 electron volt off than our excitation energy. An interesting thing about is this transition is similarly to the dielectronic satellites with the recombination into n is equal to 5. And the satellite energy is very close to the oxygen 6 plus resonance line. So I will not go into details, but what we found out that this weak 2 electron 1 photon processes are completely dominating allowed OJ and the radiative decay channels. And the 2 electron 1 photon contributions were only explained with the inclusion of large set of configurations in our calculation. And the blending, especially for the plasma modeling and for the astrophysics, the blending with the oxygen resonance line will affect probably the resonance to forbidden ratio, which is very important for the temperature diagnostics and also for the charge exchange. So at the end, I would like to thank you for attention. And this is our several works, what I have reported today. is on archive. Thank
Okay,
you.
thank you. Truly a whirlwind discussion. We are actually officially out of time, but we'll take one question from Javier Garcia. On the iron 17 discrepancy, there is one calculation, I believe by Mendoza and Bautista, that seems to be closer to your measurement. Can you comment on whether such a difference is still problematic or perhaps well within the intrinsic uncertainty of the calculations?
So as far as I remember that the value from Mendoza et al. Was something so-called fine tuning. So they used the Livermore EBIT measurement of forbidden line M2 to fine tune their atomic modeling or atomic calculations. And then they found out the value which was very close to the LCLS experiment, which you can see here. This is the value from Mendoza et al. And this is very much in agreement. But now, since we mitigate this, both of this problem, which I mentioned about the nonlinear dynamical effects plus resonant population transfer between 15 plus and 6 plus, we are actually higher than this value. So I'm not sure if this value is correct, actually.